This is the Floperator auditorium, and as you can see, it is now nighttime over here because on this side of the conference hall, it's nighttime now. Our next speaker, one of two that we have left, is Shubh Chatterjee. Shubh is a tenured data scientist and machine learning engineer who has supported database product development and problem solving across geographies and domains. Away from work, he takes his time going on long runs and reading a blend of fictional and non-fictional books. I will leave it to Shubh to explain what he's going to be talking about. So thank you very much. Take it away, Shubh.
Thank you, Tom. Hey, everyone. So in today's talk, we are going to talk about the art of categorical encoding. In today's modern world, where lots of discussion happens around the algorithm side of decisioning, that is how deep are your neural nets, how are you tuning your hyperparameters, and so on and so forth. But not much discussion happens around how are we actually representing the data to these algorithms. If you think of it, essentially, these are all mathematical functions, right? And how you represent data to these functions are as important, if not more important, than which function you are choosing. So that is what we will try to talk around in this particular talk. And yeah, we will try to finish everything in about 20 minutes so that we have some time to have some discussion or take some questions. So let's proceed. What you see on the screen right now is a simple schematic of a machine learning model development pipeline. It's a very simplistic schematic, where essentially you have raw data that you normally get from different places, different schemas, probably scraping it through the web and so on and so forth. You normally, for model development, you capture it at one place so that you can munge it and play with it. Depending upon the business problem that you're trying to solve, you will develop a model development outcome. For example, if you're developing a classifier for fraud, you will kind of develop an outcome based on that. Or if you're kind of trying to predict sales, you will kind of develop a regression based output for that. And along with that, you will also extract the predictors, which as per your heuristic or business knowledge or past model build tells you that these are the predictors for the outcome that you're trying to predict. All of this now goes into a supervised machine learning algorithm, which will give you the prediction that you are after to solve for the business problem that you want to get solved. Now, this part of the complete pipeline, right? As we started off with, lots of focus and attention goes into this part, but not much discussion happens around this part. That when you have the raw data, what are the best practices to convert them into a form and feed them into a supervised machine learning algorithm? And that is what we will try to talk about in this discussion. So let's proceed. Before we move into different methodologies of categorical encoding, a quick segue into model development data types. So when you're trying to develop try to solve a problem which is a tabular in its essence per se, you will mainly come across two kinds of variables: categorical variable and numeric variables, essentially. To keep it simple, categorical variable are variables which are probably not numeric in form. For example, academic grades, age bracket, and so on and so forth. Numeric variables are variables which are numeric in form, which you can represent on a number line, example, distance, speed, income, credit score, so on and so forth. And then there are alternate data types, which essentially are not part of a tabular data problem per se. Again, depends upon how you define it, but you can kind of do a modality shift and represent it into a tabular data problem, but we will not talk about it here due to lack of time. So let's proceed. Before we move, let's take a quick example. We're picking up a data set called the Titanic survival data set, a really popular data set on Kaggle. Essentially, what it tries to predict is for different passengers on Titanic, who might survive a Titanic disaster and who might not, essentially. That is what this problem is around. It has 12 variables. And let's look at the 12 variables so that the discussion that we did around variable types becomes more clear. One of the variables in here is survived, which is the outcome that we are trying to predict, whether a particular passenger survives Titanic or not. Okay, and then there are other variables. For example, a variable called as embarked, which tells you the port of embarkation of a passenger. It's a low cardinality categorical variable. Fare, the fare that a passenger paid to get on a Titanic, it's a numeric variable. So you get the idea essentially that for a tabular data problem, mainly you will come across either a numeric variable or a categorical variable. Now, a question that we will probably ask: why categorical variables, and why not we transfer numeric variables also? So essentially, again, coming back to the discussion that we had before, we have a predictive model, which is a numeric function per se. So you need to give it numeric input so that you get a numeric output. A numeric variable in itself are numeric in form. Of course, you can go ahead and still transform them if you want to kind of make it more predictive in nature, but it's not mandatory for you. But categorical variables, they are not numeric in form. If you want to use that information into a predictive model, you have to transform them into numeric form. So therefore, it's needed. So we will be moving to the methodologies for categorical variable transformation per se. But before we do that, we will set up some ground rules initially so that we will center our discussion around those. There are 3 pointers that we will center our discussions around. First, how much does a particular transformation methodology improves the prediction quality of a model? Second, how easy it is to implement that particular methodology in production. And third is how robust is that methodology against domain shift. Essentially, those who are probably not from the data science background, domain shift is when your real-time inference or in the wild has kind of moved away from your training data. So you want to design your model or complete modeling pipeline so that the model development is more generalistic in nature, and kind of even if there inference data changes, it kind of still remains true. So let's move to the different methodologies for categorical variable transformation. We will mainly look at 4 methodologies, essentially: one-hot encoding, vanilla count encoding, vanilla target encoding, and vanilla weight of evidence. This vanilla is something that is my nomenclature. We don't say vanilla. The reason I mentioned vanilla is all of these encoding can be done in much more sophisticated way. We'll of course cover some sophistication here, but mainly we will start off with the base things and build on top of that. Let's start with one-hot encoding. If you ask me, one of the most simple methodologies of categorical encoding that's out there, really easy to understand yourself and also to explain to stakeholders. Sometimes this is also a benefit that you should probably look into, that will it be easy to explain a particular methodology to stakeholders per se. So what you have to do in this is essentially you take a particular variable. Let's take an example of port of embarkation, same Titanic survival data set. The port of embarkation takes 3 categories: C, S, and Q. So a passenger can have port of embarkation as C, S, or Q. So in one-hot encoding, what you do is, if there are n categories, you either use n variables or n-1 variable to transform them into numeric form. For example, here C, S, and Q. What you are doing is you're converting the C, S, and Q into 3 variable: embarked C, embarked Q, embarked S. If embarked is C, embarked C will be 1 and rest of them will be 0. So and so on and so forth for S and Q. You essentially don't need n categories and n variables for that. You can get away with using n-1. Now, this is what one-hot encoding is. Moving forward, what I've done is I've used this wonderful library called as category encoders. Again, this notebook will be available to you on Git. You can post this talk and you can kind of play with it and look at different libraries I've used and so on and so forth. So yeah, coming back, I've used category encoders, and what I've done is I've one-hot encoded the Titanic survival dataset, which I had split into training and test. And post that, I have developed a model, logistic regression model. This is again another function that I have. What it does, it does nothing. It takes the training dataset, develops a logistic regression model on it, generates prediction on the training and test, and gives us 3 things: the training AUC, the test AUC, and the incremental improvement over random. Incremental improvement over random is essentially if you had just used random probabilities, what the AUC you would have got, and if you are using the one that logistic regression that you develop, what is the improvement that you have over random, essentially. What we observe is we get a 57%, close to 57% above random prediction, which is not bad, I think, for this particular use case. Again, this is a base use case, but we are looking at. Second question that we will try and answer is, how does this variable transformation methodology be supported by the technical infrastructure? Now think of this question. It again depends, right? Now the example that we looked at had only 3 categories: the port of embarkation, C, S, and Q. Now think of an example where probably there are 20 categories within a particular variable. What one-hot encoding will do is you will at least need 19 variables to represent those 20 categories. Now the compute cost when you are trying to develop a model will be high. The storage cost, if you want to store all of these variables for later monitoring, will be high. So hence, it's a one-hot encoding can be highly expensive and kind of cumbersome if the variable that you're using has high number of categories within it. Third question that we'll try and answer is, what about domain shift? To solve for domain shift, one thing that I will suggest when you're using one-hot encoding is have another variable in there, which like, for example, in the example that we looked at, it will be None of these essentially. So essentially what will happen is during inference time, if there is a category, if suppose you are using the same model on a different shipwreck data set, and if you had a different port of embarkation, that none of these will get highlighted. So at least when you're monitoring and doing something, it will tell you some information about it. Moving forward, let's look at vanilla count encoding. What vanilla count encoding is, you use the counts of each of the different categories within a variable to encode the corresponding variable per se. Let's look at an example. Another variable that is in there is passenger class, the class that passenger traveled in. So what we have done is, in the training data set, these are the corresponding counts of each of different classes in there. We just replace the corresponding categories within this variable by the corresponding counts. As simple as that. That is what we do. And even for a test data set, you use the training counts, right? Again, a modeling 101. You don't again recreate the count for the tests, because in inference time you won't have access to that, as probably we all know. So again, we did that, post that. Another question that we will try and answer is essentially what happens when in the test or inference time, if there is a category which was not in the training data set. For that, we will look at a variable called as cabin number. Okay, so what I've done here is, in the test data set, I identified the cabin number. Okay, and I saw when I'm kind of using count encoding, what does it give me? It gives me not a number, which is not surprising, because these cabin numbers were not there in the training data set. So how do we solve for that? You have to solve for it by using code. Essentially, what you have to do is, for example, what I have done in here is, when I'm using the test data set and I find categories which were not there in the training data set, I transform it into a different value. Like for example, here I've given it -9999. So we know, so the model knows essentially that this is a particular value which did not exist when we trained the model essentially, and it kind of sometimes helps in reducing the overfitting. So moving forward, what we observe is when we use count encoding, the prediction quality is much better than one-hot encoding. Again, in terms of using it for inference, much better and much easier to implement it, because each of the variable is represented by one corresponding variable, so less compute and storage cost. And third, we already looked at it, how you might handle domain shift if it happens per se. Vanilla target encoding, another really popular encoding technique. What you do is, for each of the categories within a variable, you replace the corresponding category by the mean of the outcome. Okay. So for example, again, taking the example of port of embarkation. For port of embarkation, for C, Q, and S, these are the corresponding survival rates of the passengers who had the port of embarkation as C, Q, or S. So, and what we have done is, in both in training and test data set, we have replaced these by this corresponding survival rate. Okay. Now, coming back to the question, what happens in the test data set? When in the test data set, there is probably a port of embarkation which was not there in the training data set. So the category encoder library in itself, what it does is, by default, it gives that particular category which was not there in the training category base rate, or the base probability which was there for the training data set. Okay. But again, this is something that is probably more of a default. Depending upon your use case, the data that you're working on, or your intuition, you can probably replace it by whatever you reckon. That's something that was probably not there in training, and that has now come in during reference time or test time. You might give it a median or whatever, a totally different value altogether. So yeah, moving forward, when we develop a model on it and test it on training and test data set, what we observe is, which is again not surprising, we observe a high amount of overfitting. The test AUC falls from 0.87 in the training to 0.81 in test. Okay, not surprising, because this is probably a supervised encoding technique. The first two that we observe were unsupervised encoding technique, where we never use the outcome. Essentially, we use the variable themselves to encode them. Here it is, we are using the outcome in itself, and it's kind of an observation, and probably there are lots of practitioners who have written about it. When you are using supervised techniques to encode, you might observe kind of higher amount of overfitting per se. Now, there are workarounds around it, which we will talk about as we move forward. But yeah, that's an observation. Again, the observation for inference and domain shift are kind of similar to what we observe for count encoding. Now, the next technique is vanilla weight of evidence. Another supervised encoding technique, quite similar to target encoding. Therefore, we won't go into the depth of it essentially, but it's a ratio of percentage of events to percentage of non-events within the category that is being encoded in the variable. Okay. Now it becomes easier to understand as we look at this example essentially, but yeah, this notebook will be available to it, so you can play with it. But weight of evidence is heavily used in the financial sector. Um, Again, as I said, there are lots of encoding technique, but different encoding techniques have been adapted in different sectors because, again, you can't. They have probably used it and identified that that particular technique has a heuristic advantage in those sectors. Now, weight of evidence per se, when you use it, the observations and output that you get are quite similar to target encoding because it's a supervised encoding technique. You see high amount of overfitting, okay, easier to implement, and in terms of in terms of domain shift, what category encoder library does by default is it gives a category which was in the this is in a test data set but was not in the training data set a default of weight of evidence as 0, which essentially says that we don't know about it. Again, that's a default. Depending upon your observation, you might want to change it or edit it or whatever. Now, there are some other really useful methods that I want to bring to your attention. One of them is ordinal encoding, right? Ordinal encoding is a kind of encoding which you should use if your category variable is ordinal in nature. That is, there is a hierarchy within that variable per se. That is, for example, academic grades, right? A plus plus, A, B. Okay, there is a hierarchy within it. You can give it a one. You can give it. You can encode it by using 1, 2, 3, so that when you push it into the model knows that there was a hierarchy within the variable and kind of use that information. Base and encoding, again, if n is 2, it is kind of one hot encoding. Okay, so it's you get the idea essentially. So you can similarly have base 3, base 4, and so on and so forth. Contrast coding is again useful when you have a relationship between different levels of a particular variable. It in practice, if you apply it well, essentially it improves the predictive strength of a model. Jamestown encoding, I would like to spend some time here, is a special case of target encoding. If you remember, when we looked at target encoding, there was a high amount of overfit. As I said, it was because we were using a supervised technique and directly using the mean outcome per se. What Jamestown encoding does is it tries to normalize it. What you do is you use the overall base rate of a training data set and divide the mean outcome for each of the categories by that. So what it tries to do is it tries to reduce the overfitting by using the base rate to normalize it. So in observation, in most cases, when you use Jamestown encoding, you will always observe less amount of overfitting and improvement in predictive quality of a model during inference time. Entity embedding, a really useful method. Ideally, we can have one complete talk on entity embeddings. What in entity embedding, what you do is you try to represent each of the categories within a variable into the Euclidean space by using neural nets per se. So, and then when you get this vectorized representation, that can be used into this final supervised machine learning model. And that machine learning model can be anything. That can be a boosting tree, bagging, cluster regression, so on and so forth. So essentially, you are using the power of neural nets, which essentially, in most of the cases, you will observe does not have that high predictive quality when used in a tabular data structure or tabular data problem. But you can still use them and then take out those embeddings and use them into the final supervised machine learning model. I will highly recommend this paper that I mentioned here, where the authors use entity embeddings to reduce the third position in a Kaggle competition. Please look at it. Pragmatic workarounds for problems in the wild, right? So, okay, we looked at almost 10 or 11 techniques, but I would like to bring some more notes that I have observed when I'm kind of developing models in practice per se. Cross-validation. Cross-validation is heavily used during model development, right? We talk about cross-validation during model development, but not much discussion happens around it when you're encoding your different categories or encoding your data. But in practice, cross-validation is also really useful when you're category encoding. So what I've tried to do is I've used target encoding, where you are kind of target encoding on 3 of the 4 folds of 3 of the 4 folds of the training data of the complete data of the training and test data, and 4th fold is on which you apply it. So essentially, what you do is you try to generalize it by using a k-fold cross-validation. Another advantage of this code will be available. What another thing that this code does is it also takes care of the edge cases. Edge cases are, suppose there is a category in the training data set which probably has only one observation, right? So if suppose you are using a simple target encoding, it might just use that observation and encode it, but that might lead to overfitting. So essentially, what this code does is, if in case you find such kind of categories, it gives it a not a number or 0 essentially. So what it does, it gives you a missing value, and that can later be handled when you are doing a missing value imputation. By doing this, one thing, the overall observation is that overall overfitting kind of reduces. So from the target encoding that we observed before, the test AUC was 0.8103, and right now it's 0.81569. Even for such simplistic case, essentially we see kind of reduction in overfitting. Again, there are other factors that you can bring in further improve it, but ideally in most cases in practice, you will observe if you are using cross-validation when you are doing category encoding, you will observe a benefit in your inference results. So before we close, some final thumb rules that I will kind of like to mention. Never pre-optimize. I've kind of mentioned 10 or 11 techniques. All of them can be equally good depending upon the data that you're working on, the use case that you're on, and so on and so forth. So never pre-optimize. Always try to pick up whatever is really simple for you, use that, get the base model out, and then come back and kind of try to optimize each of it. You have to remember that it's a complete pipeline thing, essentially. If you remember the schematic that I represented at the top, where you have different points where you can add efficiency to your overall model development pipeline. It's not just the algorithm part of it, or it's just not the category encoding part of it. It's important to go through different iterations, essentially, and then improve on it. Second is kind of a derivative of the first point that I mentioned. There is no perfect encoding technique. Okay, so different use cases, different data, different domains, different techniques might be useful. So yeah, as we experiment more and more, we'll probably learn more about it. And that's it from me. And thanks a lot. Cheers.
Awesome. Thank you, Shubh. We had one question, which was a couple people entered the stream late, and they actually missed what you were predicting in the models that you were using. So can you just
Sure.
Yeah.
No worries. Yeah. So ideally, the data set that we picked per se here for the discussion was a Titanic survival data set, a really popular data set on Kaggle. So it's essentially a data set from Titanic, which kind of tries to predict that what if each of the passengers within Titanic, what was the probability of their survival per se. That is what it tries to predict. Does that answer the question?
So it's the passengers of the Titanic and who
Yeah,
survived and who didn't.
yeah.
What are the inputs? What data points do they have on the
Yeah,
passengers? Is
yeah.
it
So I will go back.
demographics and
So essentially, yeah, it's mainly the different pointers. There are 12 variables in that data set. Few of the variables that exist in there are kind of just a customer identifier, like passenger ID and so on and so forth. Then there are kind of variables like the fare that the passenger paid, how many siblings that passenger has on the ship, and kind of and which was the port of embarkation for the passenger, which class did the passenger travel in, and so on and so forth. So yeah, it's a kind of blend of all these different things that kind of come together, and
yeah.
people try to predict different things. Yeah.
Cool. No, I found that fascinating because I did my postgraduate research in machine learning, and that was 15 years ago, and I haven't touched it since then. So it's always fascinating to me to see we've come an awful long way since the neural networks that I was playing with in 2005. Thank you very much, Shubh. If there are any other questions, you'll be available in the chat for people?
Yeah. I will be available. Feel free to put in any question that you might have. Yeah.
Fantastic. Yeah. So anyone have any questions, just hit them up in the chat. Cool. We're a little over time, so we have a 7-minute break before our final talk of this track. No, we actually have 10-minute break. So at 4:35, we will be back for our final talk in the Floperator auditorium before the closing keynote and the conference close, which will be in the other theater. So we will see everybody back here in 10 minutes. Catch you later.